to be here and speak about this work which I recently did with Emiliano. Title is how to get constraint on scalar fields from UV completion. And I hope you will find this idea useful, because I think it's a slightly different approach from what I've seen around. And so okay, I'll skip the outline, because it's basically directly the relevant point is to go to phenomenology, physics, force, and compact objects. But well, I wanted just to say that what I'm going to present is not really linked to proper time flow equation. Everything is actually similar and using the vectoric equation, and so therefore I think the results might be not entirely crazy, hopefully not. And well, let me remind you a couple of things that everybody knows. Scalar field theory in the equal 4. Scalar field theory in the equal 4 as massless theory in the deep ultraviolet has a Landau pole. It's no UV completion. And people usually say, okay, who cares? This is so far away that we can forget about that. Yeah, but because we are so happy in making complicated things, solve complicated problems, we really would like to ask such a question, whether even if the Landau pole is deferred to arbitrarily high energy, we would like to understand whether we can extend our theory to arbitrarily high energy, including gravity. And why this is interesting? Because if we couple gravity with a scalar theory, well, that's a very good setup, because scalar tensor theories have been used, I say, since many years. But what is, I think, interesting in the setup, that the scalar tensor theory, we found it's interesting, it can work. It's not a simple scalar tensor theory, because a simple scalar tensor theory, you can use Einstein conformal change. You can go from the Jordan frame to the Einstein frame, and that's basically an F of R theory. But what happens here to be the key is that you need something which has more than one field and less than 16 fields. So I'm a little bit anticipating what the most important result of the things. But I think this is an interesting detail, because it tells us that it's not so trivial, this type of model. So having said that, let me remind you a couple of things that everybody knows, but sometimes it's nice to remind things. We say in Italian something like repetita juvant, which is in Latin, to repeat things is always useful. And sometimes we say anche se stufant, but that's an Italian joke. Anyway, let's consider a very simple case of scalar field coupled to gravity, and with this psi, with this non-minimal coupling. And this type of action, as everybody knows, has a global scale invariance. So the action is invariant under that transformation. And in this case, if we impose scale invariance, we have already a constraint on the possible interaction. We cannot have dimensionful parameters. All the couplings are marginal. And this is a problem, because marginal coupling means logarithmic divergence, and therefore most probably Landau poles. And the theory does not select any xi. Any xi is really possible in this game. Now we can try to impose conformal invariance, which is what you see here, where omega is a scalar field, And in this case, we can easily find, that's also textbook results, that the theory is invariant under Veil invariance only if psi is 1 over 6. So in this case, we have a unique value which decides what is possible to include in the Lagrangian or not. Now we have a concept which most of the people here, I think, are familiar with, is the concept of quantum scale invariance, which I must admit I was very much inspired by several works of Christoph Wetterich in this direction. And I always ask them, I mean, this is a very, very nice idea. What happens if we impose the quantum scale invariance, if we look for scaling solutions, okay? So of course, a scaling solution is a complicated subject. We don't have much time to go into that. But if we imagine we look at the beta function in this case, we know that in this case, scale invariance can reemerge at fixed point. So is the system of fixed point which defines a set of scale of coupling for which we have quantum scale invariant. What happens in this case? In this case, what happens is that the value of those couplings are dynamically selected. And if we impose quantum scale invariant, we have even more strict possibility, we have more strict constraint on the shape of the Lagrange. And therefore, I mean, this is also what happens in turbulence, no? If classical scaling of Kolmogorov in turbulence is corrected at a nonlinear level via anomalous scaling. So the anomalous scaling, actually the anomalous, what we call anomalous dimension, is what gives the right dimension of the field. So when we would like to ask the question about what is the ultraviolet critical manifold, something like that, we do have to ask, we need to understand what is the real dynamical anomalous dimension. Well, so in this calculation, as I said, we consider gravity coupled to scalar field. We used just for technical purposes, but that was not really essential in this calculation. We use the proper time flow equation, which is a Wilsonian flow equation in the sense that it is possible to ensure that the partition function is invariant provided we have a suitable kernel suitably defined. And we use this class of regulators. Why this class of regulators? Here, M is an integer fixed by that condition, because with this class of regulators, it was possible to find rather good agreement next to leading order in the derivative expansion for the anomalous dimension near the Wilson-Fisher point in D equal 3. That's, I mean, let's say it's a purely practical choice, okay? And so now let's go to the setup. Our setup is ON theory, which is, and that's a key point where we have ON multiplet non-minimally coupled to gravity, and so because we are interested in the broken phase, it is important to distinguish between the transverse mode and the longitudinal mode. And f of rho is just a generic function of rho of the field, and we have two different transverse longitudinal wave function renormalization, because in the broken phase those two can be different. But the model you will see is not really dependent on eta. The mechanism I'll try to explain does not rely on having the anomalous dimension. We wanted to be sure that things are not tremendously wrong. And we also included the anomalous dimension. Things are a little bit more complicated, but the main results will stay. Okay, this is what many people are familiar with. We couple that to gravity and to have some hope of of uh, of um, of arriving to some final computation. We had to use basically the York decomposition with the exponential representation for the metric and the background split for the field. And then once you have done that, the key move was to use physical gauge. Okay, so the reason is that. So I'm just telling you because I'm sure that people will ask. It is possible to diagonalize the Hessians also in the broken phase. If you choose another gauge, it was really technically almost impossible to get a set of equations which was valid also in the broken phase. Anyway, at the end of the day, we had basically to introduce our set of dimensionless functions for the field, for the potential, and for the function f, and then we consider a general expansion around the broken phase of equation 6 and of equation 7. Okay. Now, yet I would like to stress that this is not really essential. We included other tabs. We did a study in another paper on looking for the most general scaling solution. But let's try to keep things as simple as possible, but of course not simpler, to understand what is the basic mechanism that I'm trying to explain. So we study the broken phase of the ON multiplet. So we have vacuum, non-zero vacuum along some component. So we have radial fluctuation, which are massive, and then we have transverse Ghorston fluctuations. So in this framework, the longitudinal scalar mass is given by the expression that you have seen here, that you see here. And the physical condition is what we see that. So then, what is the basic mechanism in this business? The basic mechanism is the following. Look, we have basically the following coupling constant: the vacuum expectation value x naught, lambda, g is basically the Newton constant here. Okay, 1 over g is the first term in front of the term. F1 is the conformal coupling, and then okay, W is the ratio of wave function and mediation function. We can just forget about that. It's not really important, as I said. And the key point is that the beta function can be separated in two components: beta g and beta m. Beta g is the matter contribution, and beta m is the gravity contribution. Beta g has this form minus a of t lambda, and beta m has that other form. And it's clear it's the competition between these two terms which decides whether we have UV completion or not. And okay, so the matter sector alone always drives, as everybody knows, basically, the quartic coupling towards singularity. Lambda grows and develops a Landau pole because all the terms in the matter beta function are basically positive. P is positive and theta is positive. So we will need something very strange, like a negative anomalous dimension to overcome that. But I think it's rather extreme. So the only hope is that the gravitational part is strong enough to counterbalance the logarithmic explosion. So Let's see what happens to the gravitational part. In d equal 4 dimension, the sign of AT is controlled by this product, 1 minus f1t gt x naught. No? So there is a critical value of the conformal coupling for which beta is greater than 0 if f1 is less than f1 critical or is less than 0 in the other case. So gravity can produce either screening or anti-screening of the depending on the value of this f1. So if we are in this case, if we have f1 is less than f1 critical, the gravity part is less than the matter part, and then we have a Landau pole. In the opposite case, here, we instead find that lambda decreases and we have no singularity. So what is happening here? To understand what is happening, we have to go to the scaling solution. The scaling solution for our system have been studied by several people. I would like to mention, even if you don't find that, Labus, Percacci, Vacca, and also Percacci and Vacca, and really we all find the same type of scaling solution. So that is to reinforce the idea that this is not cooked up by proper time flow equation, okay? And actually, we had no idea that that was possible to find this mechanism in this case, because the only difference that we really look at the broken phase, we have this class of solution, class 1 and class 2. What is the difference? Class 2 is has this term, and class 1 has no this term. So if we find that the interesting class of solution are solution of class 2, where gravity is produced. Gravity, as we know, is produced by a non-zero vacuum expectation value. And so what is this theory basically? This theory is Z theory, the old glorious Z theory in the 80s, where it was conjectured that if we couple a scalar field with gravity, and if this scalar field develops a non-zero expectation value, you can dynamically produce our gravity. And we have this fixed point, which this fixed point is as this type of structure. This is G star here. And as you see, there is N here, which is the number of fields. And M is the regulator. Well, what is interesting here? Here, the interesting thing, which made me which is a bit amusing to say, no? This is the value of the conformal coupling. Remember, we had no constraint for scale invariant, 1/3 constraint for conformal invariance, and now we have this value, which, look, for n equals 4, this F1 star is phi of 3. So do you know what is this phi? Has anyone recognized this number?
The golden ratio.
Exactly. So that means that because I trust Fibonacci, that means this mechanism must be correct. Must be something that is true in the real nature. I mean, now that's something amusing. I just wanted to share with you. Of course, we didn't write this in the paper. We said, okay, otherwise they will think that we are completely crackpot. So, but in this context, I like to share this amusing things with you. Anyway, so what is happening here? To make a long story short, that the lambda, which is usually the coupling constant, which is usually irrelevant, and then it grows logarithmically, in the broken phase becomes a relevant operator, okay? And so that is what happens for lambda. Becomes a relevant operator because it is suppressed in a very strange way, not in a power law, in logarithmic way, at t, which goes to infinity. And therefore, the mechanism that this fixed point, which only works in the broken phase, lift basically the marginality of the conformal coupling. So lambda becomes marginally relevant and is driven to zero in the ultraviolet. So that is the basic technical mechanism. So it is driven to zero, and we are attracted towards this fixed point, which is non-zero, and therefore we have basically the Z theory, the famous induced gravity theory. I mean, I am almost a boomer, so people of my age know that 20 years ago this was very fashionable, induced gravity theory in the ultraviolet. So now the question is more once we understand the mechanism, now the clear question is, okay, how do we reach this fixed point? How do we reach? And it turns out that the ultraviolet critical surface split the infrared data into disconnected region. So we have a set of initial condition for which we are guaranteed that we have UV completion, and we have this nice fixed point with the Fibonacci spiral instead of a Reuter spiral, and we have an UV complete theory. And on the other hand, if we are on the right hand side, then we cannot reach the fixed point, and we are in a situation where we basically the beta function of the matter part always dominates. So we have to find the boundary of this region. The boundary of this region is basically can be written as a critical lambda as a function of the infrared values, no, of the vacuum GF naught and W, and therefore below this surface we have ultraviolet complete theory, and above this surface we have singular flows. And well, basically that's the typical structure of UV complete theories as a function of the conformal coupling. You know? You see, this F1 can be extremely large, and you see you basically have a bound on lambda. If lambda is greater than this value, then you end up in a Landau pole. And yes, and that is you see this W is direction of the wave function, normalization function in the longitudinal in transfer sector. You can change it. It doesn't really change much this boundary. You can also change the number of fields. It works only for n, which goes from 2 to 10. And this is basically the infrared, let's say, if you see from the other point of view, the ultraviolet is the attraction of lambda as a function of psi, I mean, this basin of attraction in the deep ultraviolet region. This you have to reverse the flow, of course, of the error to be in the ultraviolet. Otherwise, you are choosing the flow in the infrared. This is really produced by the set of infrared data. This is, let's say, a focus region, set of infrared data that brings you at this fixed point. And now we wanted to connect with physics. So how do we connect with physics? How do we connect with infrared physics? This is something which I would like to say a few words more in detail, because I think that I haven't seen this mechanism really discussed in many papers in the literature. So how do we connect with we want to have a Newton constant, which is basically what we observe, that has to be constant on scales which are basically from the laboratory scale to something very high in energy. We cannot use the Planck mass to define this scale, because the Planck mass in this language, it's only, I mean, it's defined through to the value of the Newton constant, which is only consider, only define the infrared. So how do we define that? So the key point is you have to choose. And that was the numerically, let's say, non-trivial part of the discussion. You have to find a set of condition in the ultraviolet. Okay, so it is really a boundary value problem for which, when you go in the infrared, you must be close to the Gaussian fixed point, a number of EFOLs, let's say 60. So the value of your infrared G, dimensionless G, mass differs from the actual dimensionless Newton constant, 1 part to 10 to the 60 or 10 to the 70, depends what you want to what you have decided for the infrared fixed point. This is the key point, and this is conceptually and also computationally not trivial. For instance, you see what is happening here. Here you have this G is the dimensional Newton constant, which is going like k square, basically, up to this point here, where you enter the basin of attraction of the ultraviolet fixed point. And you can see we have covered many orders of magnitude, okay? And so you do have to, it is essential to describe the crossover from the Gaussian fixed point to the infrared fixed point, which defines our physics. So it is really, one might say, okay, it's a fine-tuning problem. Well, it's not different from fine-tuning the alpha fine structure. Okay, how do we know the alpha fine structure is such and such and such? Because in the infrared, we know that the mass of the electron is that one. So, the renormalization group equation can, of course, is completely blind as far as the infrared values are concerned, no? And here is, you see the running of the minimum, for instance, then you can see that the minimum runs with these things, and then it reach the value that you wanted to have in the infrared, but it doesn't really run much. So here instead you find the running of the lambda. So that is interesting. You see what happens. Suppose we start from the infrared, t is log k, no? That's a value of, of the lambda in the infrared, and you see this grow is basically the logarithmic grow, which starts to pile up around this region, and then you are basically attracted. You have a switch of a sign in the beta function, and you are attracted in this towards is very far away lambda equals 0, let's say fixed point value. And the same happens with F1. We do have to expect this grow here, because F1 is marginal. So this is really a logarithmic grow. When I started discussing this thing with Emiliano, I said, okay, but if we have no hope to find a UV complete gravity, because even if we have the Landau pole, then the conformal coupling will blow up, and we will have something which is not ultraviolet completed in the scalar tensor sector. And with our really surprise, we found that the same mechanism that is operating for lambda. It's also operating for the conformal coupling, which has this transition from the, let's say, standard logarithmic growth to a decaying phase where you reach your Fibonacci fixed point. So we have Fibonacci fixed point for F1 and Reuter fixed point for G. Anyway, so the running of the longitudinal scalar mass I will skip because this is something that Emiliano discussed some times ago and in his model. Well, there is a bound for the mass, for the scalar mass, but of course we cannot claim that it has anything to do with the standard model. So let's go to fifth force and compact object. So in the theory I discussed at the beginning, okay, so it's a scalar tensor theory with basically we have some Goston bosons which are basically decoupled from the system because they are only derivative coupled with the system. When we have a transverse mode instead to the system, which doesn't carry any charge, but it does produce a fifth force type of correction in the gravitational sector. Well, that's interesting because now we look at real data, and alpha y is the strength and lambda is the range. So what we had to do is to basically rewrite our set of infrared allowed values for x naught, lambda, g, and f1 in terms of these two parameters. And of course, there is some freedom in doing that because F1 can be arbitrarily large. We don't have much constraint on F1 unless we use it for inflation, which this is not the case. And we use our, let's say, numerical construction of the ultraviolet critical manifold to constrain those values. And it turns out that there is a very clear excluded region in this in this space, basically this is a plane of strength versus the mass of the length of the Yukawa force, constrained by various possible experiment. And you can see here there are lots of possibility. I know that string theory is one plan. People think that here there should be something related with the moduli space stabilization in this region, and it turns out that if you impose that the Newton constant stays constant basically from the Planck scale to laboratory scale, size scale. I mean, this is we choose electron volt, but if you go 0.1 electron volt or 10 electron volt, it basically doesn't change much. It turns out that this part, the left part of the plot, can be excluded by ultraviolet completion, and this is, I think, it's a very precise, very concrete prediction for this model. Let me say, for asymptotic safety, as we understand now the theory today. And therefore, we can try to speculate whether this can be seen in some experiments, like at the planetary scale or even galactic scale, of course, that is even more difficult. But I would say that if in this region, laboratory scale, we will find something, this might be a problem for asymptotic safety. I mean, it's possible to, let's say, kill the theory. It is really possible, okay? And that's the first message. And the second message is that we might construct a model to have dynamically a regular black hole core. Because you see, in the ultraviolet scaling regime, the scalar approach a constant configuration. So the gradient are zero, U is zero, and the effective action reduce our effect to this form, where G effective is 1 over star minus 1. Okay, and we have an effective lambda cosmological, let's say, vacuum energy. And therefore, we get for, let's say, in quotes, for free, a de Sitter interior. So at the low, let's say, at very low energy, we expect to have gravity as we know, and we must have a Schwarzschild exterior. But if this mechanism works also at very high energy, we might expect to have the de Sitter interior in force case which are close to this fixed point. So I would like to remind you that this fixed point exists only for n greater than 2 and n equals 16. So in the case of interacting multi-component scalar sectors. And yes, that's something interesting because we cannot map this theory in a scalar tensor theory, in an FOR theory. It's something really new, something different. And this idea suggests that we might look, it makes sense to look for self-gravitating scalar configuration with induced gravity, like for instance boson stars, or scalarized compact object, or even a regular black hole. And well, I don't want to speculate too much about the possible application of this idea. And I think that the conclusion are the following. If we consider n scalar non-minimal field coupled to gravity with the proper time, but I said that's also same fixed point is also present with the vectoric equation. What we find that the gravitational fluctuation can overcome the Landau pole problem and therefore we can actually define a region of infrared boundary condition for which we have ultraviolet gravity domination and UV completion. Our fixed point is given by this structure here, which is for n equal 4, which guarantees that we do have regular trajectories. If let's say, as a proof of concept, we would like to apply this to infrared to a scale which is the scale of the top. In this, we discuss this possibility as a really toy model because we don't have fermions. But it's interesting to show that the mass of the scalar is of the order 128 gigaelectron volt. And in the case of a scalar theory, of a scalar tensor theory, we might restrict the strength and the length of the Yukawa correction. So the take-home message is that quantum gravity, as it implemented in this discussion, tell us that only restricted set of scalar tensor theory are possible, which will leave real signatures in both particle physics and gravity. Thank you for your attention.
Thank you very much, Alfio, for the nice talk.